Welcome back, everybody. We're going to talk today about mechanical advantage components. So, welcome. We're going to dive right in here. This is a long slide deck. I'm not going to spend too much time on every single slide that's on here, but we need to kind of review a little bit about mechanical systems, mechanical advantage, and then get into basically belt drives and chain drives as well as some linear drives. We'll probably split this subject matter up into several videos, so I'll be picking some choice spots to pause and go on to the next subject in another video. So, mechanical systems. First off, the basic element of any mechanical system, and this is everything from chains, belts, gears, all of them rely on, like at its core, on leverage. So leverage is the idea of using a straight item that has a fulcrum to it. And there's various different classes of levers, and we're not going to expect you to memorize all of the technical jargon around it, but it's good that you kind of know that there's essentially three types of levers. So, for instance, this is your classic sort of seesaw lever, right? Where you have the fulcrum in the middle. A class 1 has the fulcrum in the middle, and the effort is applied on one side of the fulcrum, and the resistance or load is on the other side. So you see this as a seesaw, a crowbar, a pair of scissors. Plain and simple. And the distance between the fulcrum and the effort and the resistance is going to tell you exactly how much mechanical advantage you get out of that. Class 2 is the resistance is in the middle, and the effort is applied on one side, and the fulcrum is located all the way on the other side. So if you take a look at this picture here, think about a wheelbarrow. So you're applying effort, and then the resistance is more towards the middle, and you're able to handle a heavier load because of the length of that from the resistance, the length of your effort from the resistance. Then you have class 3, which is effort is in the middle. Effort is being applied in the middle. So essentially, an example of this would be a pair of tweezers or your jaw. That's what mandible means, by the way. And there's various other mechanical elements that you'll see, such as a crane, an excavator, etc., that use this sort of thing. But essentially, the fulcrum is behind the effort, and the resistance is out in front of the effort. So the mechanical advantage is different depending on which class it is. You can have a mechanical advantage that is greater than, less than, or equal to 1 with class 1. In class 2, the mechanical advantage is always greater than 1, so it's called a force multiplier level. And a class 3, because you're applying effort in the middle, it is also called, the mechanical advantage is always less than 1. It is also called a speed multiplier level. So each one of these things, little different as far as what it allows you to do with mechanical advantage. So speed and torque basically share this relationship, right? It's the same sort of relationship as distance and power. So torque, though, is when we start talking about torque, this is just applying the linear motion that we get out of a lever. And if you think about it, each tooth is essentially levering the tooth of the opposite gear. So that's where leverage is being applied there. So it's the same mechanical relationship. between speed and torque as there is between distance and power when it comes to just sheer leverage. Torque is the rotational force measure in either Newton meters or foot-pounds. And speed is measured in rotations per minute when we're talking about rotary speed. So those are two items, and like what we do with levers, when we do it with gears and sprockets and belts, we are trading off speed for torque or torque for speed. So we talk about ratios. So the gear ratio or the belt drive ratio or the chain ratio, the gearing ratio is the relationship between the two numbers that indicates how many times the first number contains the second. The ratio of A to B. So you might hear these being called the antecedent and the consequent. That's actually pretty rare. For belt drives, A is always the driver and B is always the driven. But there are other systems where that is not the case, where you can have either A or B be the driving, the one that has power applied to it, and B being the driven, and the driven being the one that is being powered by whatever is spinning A. So the driver would be what you would attach to a motor. B would be, or the driven would be what you attach to an output. So let's start talking about machine elements here. And we're going to talk about belt drives first. It's kind of one of the most simple ones. They rely on friction. A sheave is essentially a pulley. It's essentially a pulley with a grooved wheel for holding a belt, a wire rope, or a rope. And so that's what we call that wheel that you see in a pulley. It's a sheave. And this gives you a good diagram. You can kind of examine this on your own time to get a handle on some of the terminology involved in it. There are various different types of belts. You probably have seen V-belts, but there's many different varieties of belts, from flat belts to V-belts, to all kinds of ones that are lugged as well. Belt drives are one of the most cost-effective and easy to use ways of transmitting power from one shaft to another. In fact, it was like in the first, when industrialization first started to happen, belt drives were the way in which you'd have essentially like one power shaft that was coming off of a water wheel that drove all of the machinery in the mill. And that would just be one long shaft, and then you would just draw belts off of that shaft in order to transmit power to individual machines. They're very low cost because it's just a belt, right? And that belt, you know, it could be, like, most of the time they're kind of steel belted rubber these days, but you can have just plain rubber ones. You can have ones that are made out of leather. You can have ones that are made out of rope, really. But the vast majority of them in industry today are made out of rubber that is generally reinforced with some form of steel. The entire way in which they transmit power is due to friction. The belt itself meets the sheave, and it's because of the friction along the sheave that it is able to transmit power. And this leads to one of the significant limitations of belt drives. So you can have belt drives that have multiple geometries about how the belt is wound around those sheaves. So if you take, for instance, the non-reversing open belt that you see at the top, that goes in one direction. And the way the input rotation direction is the same as the output rotation direction. With the reversing one, because we crisscross it, we can actually reverse the direction. So the input direction would be the opposite direction of the output. And then you can have a reverse crossed belt or a reversed open belt so that it's not crossed over. So you use a couple of idlers. So those little rollers that are off to the side there are that. And then you can do things that will cause an angular change as well with a belt, depending on the belt geometry itself. So open belt drives are used, and these are by far the most typical. If you've ever looked at, well, I mean, this kind of like what you see on a table saw or any sort of other relatively inexpensive piece of machinery. You've got a top side of it, and basically the driver is driving and it is pulling. The driver pulls on the tight side. So if you take a look at this counterclockwise motion of the driving belt here, you'll see that because it's pulling, it really is only transferring energy along the top there. The energy is not being transferred along the bottom under the slack side there. So you'll see the slack happen on that. And then you'll see what would happen if we reverse direction on that. Is that then it's pulling from the bottom and it's kind of throwing the belt back around on the slack side. The danger of this is that you really don't want to have the slack side be above the tight side. So if you're orienting this vertically like you see it on the screen here, gravity could cause the slack side to hit the tight side. Whereas if you have it driven the way that is shown on the top, you will see that the slack side is free to sag as much as it needs to, and it won't ever collide with the tight side. The cross belt, obviously you cross them over and it causes counter rotation in the opposite direction. You can have quarter twist and twist drive belts, and you can have a right angle drive, and there might be a guide pulley in there to make it go around that corner. Yeah, the face of the pulley should be 1.4 times greater than the width of the belt to prevent the belt from slipping off of it. Obviously, if you're going to change the angle, you don't have that alignment that's going to keep it kind of center in there. It's really kind of key when you do these that you have a pulley that's much wider than your belt. And you can have compound drives where one belt leads to another and leads to another. And this is how we can go from one shaft to another number of other ones. And this allows us to have multiple speed settings, because one of the things about belt drives and chain drives is that you can't have you have an upper limit of the mechanical advantage that you can get out of one, and it's usually it's a factor of 3, because otherwise the difference creates an angle so that the angle that you see here between the small sheave and the large sheave, that becomes so great that it loses friction on the smaller one because there's less belt in contact with it. So the advantages. Belt drives, simple, economical. They do not require parallel shafts. The noise and vibrations are minimal because compared to a chain or a gear, because it's kind of a flexible material that's transmitting that. They have a high resistance stored stress from load fluctuations, which is one of the reasons why you'll see them used in table saws, etc., rather than the rigid, more rigid drive systems. And they're lubrication free, which is kind of nice. Less maintenance cost. The disadvantages, because it relies on friction, the angular velocity ratio is not necessarily constant or equal to the ratio of the pulley diameters, because they'll slip and they'll stretch. They're heat and moisture sensitive, so that's a bit of a disadvantage. And they can't power larger loads. You can't really do a larger load because it will essentially cause the belt to slip. You can add more friction into the system, but that friction, in essence, adds less efficiency. You're transferring less of the power through. So it's not really great for big loads. It's okay for small loads. All right, so if we calculate the belts, calculating belt speed is an important thing here. We're going to be working with conveyors in this class. So a conveyor belt is really just a belt drive system, right? So if we look at it, we want to measure if we're talking about a conveyor belt, we're talking about something that is measured in surface feet per minute. So it's how much belt is traveling across a finish line per minute. So in order to calculate that, I've got the equation below. This is one that you might want to take a look at because this is going to enter into how we speed our motors for this class. So you have to take the diameter of the pulley and the RPM of the pulley, and then the conveyor would be this according to that equation. So the surface feet per minute equals 24 inches times 200 RPM, et cetera, et cetera. And then you would divide that by 12, and you get 4,800 surface feet per minute. In some cases, conveyors are designed to run at a specific SFM for a particular product. In this case, it may be chosen based on the specific requirements of the product, how fast it's going past a labeler or a printer in whatever plant that you're working with, rather than being calculated using the diameter and RPM of the pulley. So you can essentially work your way backwards by altering the hertz that you supply, the VFD. The VFD supplies the motor with, so that it can adjust it to the exact surface feet per minute. And so you can create a feedback loop that way rather than doing the calculations the other way from an RPM. So we'll get more into depth on this when we're in person and we're dealing with a conveyor and conveyance systems, because those are belt drives. And we'll talk about chain drives in the next video. So we're going to take a quick break. When we come back, we'll talk chain drives. Not all that different, just a little bit different. We'll see you in the next video.